Hello, Didier Stevens here, analyst at Enviso. At Enviso we did research into the encrypted network traffic of Cobalt Strike, so the traffic between a beacon and the server. And we found methods to decrypt that traffic. Under certain conditions it's possible. We wrote a series of blog posts over on our blog, so blog.enviso.eu. You can find a series of blog posts. The first one talks a bit about the encryption, how Cobalt Strike does its encryption with RSA and AES, and also the fact that we found private keys that we can use to do the decryption. And then there are follow-up blog posts for different methods to do the decryption. And here I'm going to make a couple of videos that show you the methods as they are described in the blog post. So here in this video I'm going to start with this blog post, part 2, where we use a known private key to decrypt traffic. As you can see here, I'm using Wireshark and Python tools in this blog post. What I'm going to show in this video is slightly different, so that you have actually a variant of the method. Instead of using the console version of Wireshark, so Wireshark, I'm going to use the console version of Wireshark, so that is known as T-Shark. So I'm going to do everything from the console, but do know that it's exactly the same method, except here Wireshark is used. So let's get started. So, as is mentioned here in the blog post, we are working with a PCAP file that is publicly available from Duncan, senior handler at the Internet Storm Center. And this is a PCAP file here with Cobalt Strike traffic, so that's what we are going to look at. I have that here, and the zip file, and I extracted the PCAP file. So now I'm just going to run T-Shark on it. So that is in the Wireshark folder here on Windows. And I'm going to read the PCAP file. And then you get all of this output. Now, let's assume that we don't know anything about that PCAP file, that the only thing that we know is that it contains Cobalt Strike traffic. So we are going to look for URLs that might be indicative of Cobalt Strike. If you use option V, that is verbose mode, and then you see the full packet dissections, as you can see them in the dissector pane of Wireshark, but here it's in the console. And so in here there will be URLs. I can grep for that, like this. Okay, and I'm getting a bunch of URLs. So some of them have a format that might indicate that we are dealing with Cobalt Strike. And for that, to detect those URLs, I have a tool, Metatool. Metatool is a tool that can recognize some schemas used by Metasploit, hence the name Metatool, and Cobalt Strike also uses some of those schemes. What we are going to look for are URLs with a path that have a certain checksum 8. So that's done with the option URL 8, and here 2 URLs have been selected. So here that path ABHM, if you calculate the checksum 8 of these characters, you end up with value 5C, so in hexadecimal 5C. And 5C, that is the value that Metasploit uses for a Windows payload, or that Cobalt Strike uses for a 32-bit Windows payload. So this is a very strong indication that this is the IP address of the Cobalt Strike server. So let's filter for that. I'm going to add a display filter to the T-Shark command, so I'm filtering for HTTP and the IP address attdr equal to this here. Okay. Okay, and we get that. Let me interrupt this and page this. Okay, so here we have our get, and then a BHM, so that's the stager payload that is being downloaded. And then here we have a bunch of returning requests. So this could be Cobalt Strike traffic. Yeah, and here we have a post with a submit. Yeah, so this definitely looks like Cobalt Strike traffic. So that is the IP address here of the C2 server, and that here is the IP address of the agent, the beacon. So let's try to extract that payload. So the Cobalt Strike beacon that is downloaded here with this first command, and then we can analyze it with our tools to be certain that it is indeed Cobalt Strike. So this can be done by exporting HTTP objects, and that's what I'm going to do here. Export objects with T-Shark objects. So I want all HTTP objects, and I'm going to store them in a folder that T-Shark will create for me, HTTP OBJs. Like this. No. A typo here, sorry. Export objects. Okay. And here all those objects are being exported. And we get a virus alert, which is a good sign. Tells us that we are most likely dealing with malicious traffic, because when one of the objects was written to disk, it was detected and removed by the antivirus. So let's look into the folder. Yeah, indeed a lot of files. Let's sort this by size. Okay, and here we have our ABHM file, which is about 200k. That's typical for a payload beacon that is downloaded. So I can analyze this with a tool 1768. That is a tool that can analyze Cobalt Strike beacons and extract the configuration. So let's see if this works here. And indeed it is able to extract the configuration. So this is now a certainty that we are dealing with Cobalt Strike, and that is indeed the payload that was downloaded, so the beacon. So I'm going to save this output to a text file that we can have a look at it afterwards, because I'm going to remove all these extracted objects just to avoid having more antivirus alerts. Like this. And now we can have a look at the extracted configuration. So indeed it is a Cobalt Strike beacon. It's an HTTP beacon, port 8080, and that is what we saw. This is the public key, the public RSA key that is used to encrypt the metadata. And here, important information: for this public key we also know the private key. So you have malicious actors, and that is what Brad captured here, a malicious actor at work here on his honeypot, on his sandbox machine. You have those malicious actors who use pirated versions of Cobalt Strike, and some of those pirated versions also are distributed with a public and a private key. And normally this is generated at first time use of Cobalt Strike and is therefore unique for every instance. But there are pirated versions that circulate that already contain the public and the private key. And so these keys can then be extracted and used to do the decryption. And that is what my tool here tells us. This has a known private key, so we can do the decryption. This is the IP address of the C2 server, the Cobalt Strike team server. That's what we also saw in the capture packet. PTG for the get, that's also something we saw. And then submit.php for the post, also something we observed. So, since we know that this is Cobalt Strike and that it uses a public key for which we have the private key, we can start the decryption of the traffic. So let's go back to T-Shark. Again, do a verbose command so that we have all the outputs. And the encryption keys, AES encryption keys that are used for the Cobalt Strike traffic, those keys are stored in encrypted metadata. Encrypted metadata that is sent to the C2 server under the form of a cookie, an encrypted cookie. So let's grep for cookies. Okay. A lot of cookies here, but they all are the same, apparently. Well, I'm just going to interrupt this because we just need one of those cookies. Okay, so here you can see cookie pair, and this is the value. And if you take a close look, yeah, this isn't actually a real cookie. This is base 64, and this is the encrypted metadata that is represented in base 64. So I can copy this and then decrypt this with a tool that we developed, CS Decrypt. Yeah, CS Decrypt metadata. We pass it a cookie, and here is the decryption. So the tool is able to do the decryption because this encrypted data is encrypted with RSA, with that public key, and the tool here, for that specific public key, the tool also knows the private key, and because the tool has the private key, it can do the decryption. So metadata starts with this header, so that's how we can recognize that indeed we were able to do the decryption. And here you have the keys. This is the raw key. That is something we will use to the decryption. And then there is more metadata, like the internal IP address, the name of the machine, the name of the user, the name of the process that is hosting the beacon. So that's a good sign. We are making progress here. So let's copy this raw key. And now we can do the decryption of the data with that raw key by running the following tool, cs parse traffic.py. Now, if you read closely the description of blog post 2, so this blog post here, so here you see explanation of CS Decrypt metadata, and if we go further down here, you have decryption of the data itself that is done with CS parse HTTP traffic, while here I'm using CS parse traffic, so no HTTP. So the story is the following. This is a beta tool, and this is the final tool. This tool is capable to do HTTP but also DNS, and that's for an upcoming video. So you can still use the beta tool, but I recommend that you use the new tool here, CS parse traffic. So we give it the raw key, and then we just give it the PCAP file, and then it will try to decrypt all of the HTTP traffic that it finds in that PCAP file. Okay, here we already see something. So the decryption works because we saw the content of a directory. Uploading of files. Okay, and here a crash. A crash because it is not able to do the decryption. Now that is something to know. The tool here is trying to decrypt any HTTP traffic that it sees by default. So also traffic that is not related to Cobalt Strike, and that is why we have this crash. So to avoid this, you need to filter for that Cobalt Strike traffic, and so you can just use that same filter here. So the one that we used in T-Shark, I'm going to copy that one, and that's the one that I'm going to use here, like this. So parse the traffic, decrypt it with a row key here, only look at HTTP traffic for this source or destination and do the decryption. Again, here we see the content of a directory, so decryption is working. Uploads. Here we get an error, so that is an error that is sent to the Cobalt Strike Steam server by the beacon. This looks like a process list. Okay, and then at the end we get an overview of all the commands and the callbacks that were found. So commands sent by Cobalt Strike team server, so by the criminal, the commands executed by the criminal, and then here callback, so data output that is sent back by the beacon to the Cobalt Strike server. And we see command like sleep, cd, ps, ls, drivers, rm, uploads, execute jobs. And here in the output we see, for example, also port scan. So one of the jobs was a port scan. So let me pipe this to another result, like this. Then I can page through it. Okay, so let's page through it. So here we have command sleep that was decrypted, so that is sent by the team server to the beacon. And this here sleep 100 jitter 90 tells me that this is an interactive command, so to make the beacon interactive. And then we have an ls command, so a directory command, to give all the files in the current directory, and that information is then posted back by that submit, and the decrypted information here is this folder, so it is inside the documents folder of that user. That is all that being sent back. Then we have a cd command to program data, then again a directory here, and that is the content of program data. And then we have uploads of here a PowerShell script split in several uploads, and here is the content of that script, a lot of base64 like it looks like. And other uploads. Okay, and then here we see the execution of that script. So cmd c PowerShell hidden window execution policy bypass, and then execution of program data rs.ps1. And here you have the output. So that is the output here of the PowerShell script. Displays the directory, some information, and then we get an error with get content cannot find drive, and then an error output. And then next what the criminal does is to delete that PowerShell script, and then he tries to execute more jobs, like here in NetView domain, where that fails. Here We see the result of a port scan that was initiated. So a lot of interesting information here in that capture file. So this illustrates the method here to decrypt Cobalt Strike traffic, HTTP traffic here. If you have HTTPS, you can also decrypt it, but then you need the decrypted HTTPS traffic. So that layer of TLS has to be decrypted, for example, by doing interception of TLS and get the unencrypted commands, unencrypted HTTP traffic, and then you can do the Cobalt Strike traffic the same as here. And we were able to do that because this beacon that I selected here, that malware traffic that I selected here, uses a beacon that uses a public key for which we have the private key. And you also have the private key because that is included in the tools, which are free and open source and can be found in the GitHub repository.